Right, good morning. So we're going to finish our discussion of rotational motion today by considering two final examples. So the first one is just a demonstration of a problem involving both rotational and translational motion. And translational motion. So the problem expressed concerns where to find the sweet spot of a cricket bat. So if you're a visitor to this country and you don't know the wonderful game, it applies also for a baseball bat or indeed a tennis racket. So there's a place where you can hit the ball where it flies off and everything is particularly wonderful. So we want to calculate where that point is. So it needs a little bit of thought to understand what the condition is. But actually the condition is that the top of the bat, where you're holding it, that should actually feel no instantaneous force. There should be no acceleration of the top of the bat. Okay, so what this means is that the velocity of the top of the bat from the translational velocity must equal the velocity due to the rotation. So that there's I inherited this slide, so there's an attempt, there's diagrams here in different frames. I think this overcomplicates the issue, so let me just draw the situation more simply here. So this is the bat, so this is the handle. It's a very idealized bat. Okay, this is the center of mass. And the ball hits it at some point, gives the force, and the point is a distance x below the center of mass. Okay, so the deal is that this imparts both translational and rotational motion. Okay, so the center of mass of the bat, and indeed the whole bat, will start to move in this direction, but because it's being struck in general below the center of mass, it will also exert a torque, and the bat will start to rotate. Okay, so there's impulses which are given. So the translational, the change of momentum will be the external force, which is F times the time over which it happens, and then and this is the impulse on the center of mass of the object, and then there'll be a sort of rotational impulse, so an impulse in terms of angular momentum. So delta J is evaluated around the center of mass. And this will be given by the torque, which in this case is going to be just x times F times delta D. Okay. So what we wish to do is to balance things. So top of the bat doesn't move. Okay, at least initially. Right. So how can we do this? Well, let's consider the translational motion first, because that's straightforward. So the force to the Cm is just given by F equals ma, where m is obviously the mass of the bat. So the acceleration, and this is the translational acceleration, of course, is equal to F over m. So this is the acceleration of the bat. Okay. So the centre of mass moves with that acceleration, but of course the whole bat moves with the centre of mass. Okay, now what about the rotational motion? It's going to be useful to know the moment of inertia. So the moment of inertia of this object. So we calculated such a thing yesterday. So the moment of inertia with respect to the centre of mass is given by a 12th mb squared, where b is the total. Should have put it on the figure, but it's too far away now. But b is the total. Is this defined somewhere? It should be the full length of the bat. Yeah, I have a b over 2 here. So b is the full length of the bat. So annotate that picture. Right. So the torque about the centre of mass is going to be given by it's going to equal ICM theta double dot. This is just Newton's second law couched in rotational terms. And we said that the torque is equal to x times F, okay? So if we put this information together, we see that theta double dot is equal to 12fx over mb squared. So that's the rotational, so that's the angular acceleration. Right, so to try and, so we want to balance that against the translational acceleration. So again, to be clear, so the bat is going to rotate in this direction while at the same time as moving backwards. So to balance these things, we need to equate them, but this is an angular acceleration, so we need to turn it into a spatial acceleration. So the acceleration of top of bat due to the rotation is just going to be given by this multiplied by b over 2. And that equals b over 2 theta double dot, which is 6fx over mb. Okay, so this balance condition, so such that the top of the bat does not move, is when we equate this to the translational acceleration. So F over m equals 6fx over mb, and so x equals b over 6. And this is the distance below the centre of mass of the bat. So if we calculate the distance from the top of the bat, so this is 2/3 of the way from the top, which seems about right if you can picture a cricket bat in your mind. Okay, so for our second and final problem of this nature, again, I'm afraid we're having to span lecture sheets, but we are about to resolve that problem. So if you can go to the next lecture, we start with this problem. Okay, so you can, let's see what's going on here. So it's about aircraft landing and focusing on the wheels of the aircraft. So they're big things. We approximate them as a circular disc of diameter 1 meter and mass 200 kilograms. The aeroplane has 10 wheels in total, and we propose it is 100 tons. It lands at a speed of 50 meters per second, and we assume at that moment that as it's landing, the wheels support 50% of the total weight of the aircraft, because there's obviously still some upward push from the air under the wings. Okay, so it says determine the time duration of wheel slip if the coefficient of friction between the wheels and the ground is 0.5. And we should assume that the speed of the plane is not changed significantly. So what do we mean by wheel slip? Because that's maybe not entirely obvious. Well, the point is that when the plane lands, as soon as the wheels touch the ground, they start to revolve, but they will not be revolving at the speed the plane is going initially. So they'll be spinning around, but they won't have caught up with the plane, so they will be slipping on the ground. But eventually, they will be rotating such that their translational speed is the same as that of the plane. Okay, so the wheel slip is the period in which the wheels spin has not caught up with the plane velocity. Okay, so I hope we understand what's going on, and now we can try and tackle the problem. What happens when the plane touches down is that each wheel will, there'll be a torque on each wheel, and that torque will come from the friction imparted by the ground, okay? So I call m prime the mass down. We'll define what that is in a moment. Mu is the coefficient of friction, and so there's this force mu m prime g, which will exert a torque of that multiplied by A. Okay, so torque is A mu m prime g, where m prime equals the total mass divided by 20. Why 20? Because we have 10 wheels, and the wheels support half of the total mass of plane mass. Okay. Right, so we have a torque, that's great. What is torque related to? Torque is related to the rate of change of angular momentum. So torque equals dj by dt. We're interested in the velocity at which these wheels spin. So that is, so J is I times omega, so I moment of inertia, d omega by dt. And what we're really interested in is the actual real velocity, the translational velocity with which the wheel is spinning, which is designated as u there. So that's clearly related to omega by I over A du by dt, where maybe I'll just where u is the velocity of the wheel rim. Okay. So initially, just to be clear, the actual wheel, the centre of mass, is moving initially faster than that because the plane, when it lands, is moving faster than that. But this is the velocity with which the wheel rim is spinning. Okay. Right. So I remind you, what we're after is to try to calculate the time it takes for this wheel rim velocity to reach the velocity of the plane. So we have a differential equation that du by dt is a squared mu m prime g. Oh, there's an I involved here as well. I on the bottom. Yep. So we can solve this. It's very straightforward. So separating the variables, du equals the integral over time of all of this stuff. And what are the limits? Well, we start at t equals 0, and we end up at t, let's call it tf, t final. It starts with the wheel not spinning, and eventually it reaches v0, where v0 is the landing velocity of plane. Okay. So that's a very easy equation to solve, and we get to that Tf is V0 I over A squared mu m prime g, and let's put in what I is. I is a half ma squared. So that's the moment of inertia of a disk, which we evaluated yesterday, and little m here is the mass of the wheel. It's not, okay, so we need to. That's different from m prime because the mass of the wheel is different from the total weight downwards. And so Tf is given by V0 little m over 2 mu m prime g. Okay, let's give this let me give this a. Have we got this right? Yeah. Let me give this. Let me also write down, which is the previous step, what the velocity v0 is before I invert this. So this is absolutely trivial, but it's just because we will use this expression a bit later. I should have written this first. Okay, sorry about that. So that really comes before then, and then we have this. And I want to number these because we will. I will reference these later. So I call this one 1 and this one 2. Okay, but this is what we were wanting to work out here. This is the time it takes for the rim of the wheel to reach the same velocity as the plane. Okay. Now we were given numbers. Here they all are. So let's put in those numbers. and you can see that we get TF is about 0.2 seconds. So it happens rather quickly. The wheel slip is a very, very brief interval of time. Now, what will happen naturally is as the thing is landing, it will be the plane will be giving energy to the wheels, because the wheels start with no kinetic energy, and then they, apart from the translational kinetic energy, but they start with no rotational kinetic energy, but then they start to spin. So that energy must come from somewhere, and it comes from the plane. So this business is actually going to be slowing the plane down. So in reality, the velocity v0 will change over this period. Okay, now we were told to assume that it wouldn't. That was an assumption which was on the bottom line here, assume that the speed of the plane is not changing significantly, but clearly it will be. So it would be a good practice to check whether this assumption we made is a reasonable one. Okay, so let's check by how much this change of velocity is. Okay, so we're now confirming the assumption that the speed of the plane is not changed significantly. We're going to calculate the change of speed at the end of the wheel slip. Okay, so but firstly, to say, let's solve this in terms of energy. So the energy expended in getting the wheels up to speed is what? Well, the E rotational of the wheels when it's got up to full speed is going to be given by 10, because there's 10 wheels, times the kinetic energy of the rotation of each wheel. And remember, kinetic energy for rotational motion is given by a half I omega squared. So a half I omega squared. And let us remember, what is omega? So omega is equal to v0 over a. Okay, so that's the final velocity they reach, on the assumption that that doesn't change much. And I, as before, is a half ma squared. Hence, this energy, this rotational energy, is given by 5 over 2 mv0 squared. Now, as the plane is landing, just before the plane touches down, what energy does it have? It's just kinetic energy. So, so the Ke of the plane, let me just write that as E, that is given by a half big M v squared. And so if we assume that the plane, as it lands, it loses a little bit of energy, just a little bit, so the energy loss, or energy change, but it will be a loss, we can write as delta E equals dE by dV delta V, okay? So that is mv delta V. And so what we are interested in is delta. So this must be equal to, where has this energy loss gone to? It's gone to the wheels, so this must be equal to 5 over 2 mv naught squared. Okay. So, and when it's landing, this v is approximately equal to v naught. Hence, we can write down the fractional change of velocity, delta v over v naught, and that will be given by 5 over 2 little m over big M. So again, we can put in the numbers, and we find that this is 0.5%. So this is small, so the approximation was good. Okay. So there's one final thing I want to do in this problem, which is calculate the actual work done during the wheel slip. And if you're still awake, the actual answer we end up with should be obvious, but let us, not to give a spoiler to those who can't see this, but let's see if we do get the answer we expect. So the work done during wheel slip, and this is a good exercise because it enables me to write down this expression here, which I think we've, yes, we have seen before, but maybe not used very much. So for rotational motion, well, for translational motion, work done is the integral over force times distance. So for rotational motion, it's the integral over torque over the angle change. Okay. So we need to know the total angle change. And we're going to, so we can write this as a straight multiplication because the torque is a constant, because the torque just depends on the mass, so that doesn't change. So we can write this as a straight constant, and so it becomes an integral over delta theta. So I've written theta f, and theta f is the total turning angle. Okay, so that's how much the wheel turns by, and we assume that the wheel's going to spin a lot, so it will be more than 2 pi, but that's still allowed. Okay, so so how can we calculate this? So we need to work out what theta f is. We know what the torque is. So before we know that we have an expression which involves theta, and that is just u equals a d theta by dt. Okay. And so, yeah, but u we know, and you say, well, how do we know it? And I think I will push this up because we just have it. Okay, it'll just, right, we know, and this is from expression 1 in the general case. So I think I can push this up, and we should be able to see both this board and expression 1. Yeah, just about. Okay, so I said this was, we'll be using this later, so this is when we did that, solved that first equation, we got an expression for the velocity. That was, we designated this as the velocity at the end of the wheel slip, so we wrote that as v0. So in the general case, I'm going to use this expression, but just write u here and t there, okay? So let me demonstrate. So we have that u equals a d theta dt, which is the same as what we had in expression 1, which is 2 mu m prime gt over m. This is from 1. So I hope this is the same. Yep. Okay, so this is now nice because we're after an expression for theta, right? So now we have another differential equation to solve. So we have d theta by dt is equal to 2 mu m prime g t over little m a. And so, again, separating the variables, we have that the integral of in the way I've got it in my notes, I keep the a on this side. So the integral of a d theta between 0 and theta f is the integral of this stuff over time between 0 and the time it takes for the wheel slip to occur. So between 0 and tf. Okay, so we end up with a theta f is 2 mu m prime g t squared over 2m. So actually, I'll get rid of that 2 there. And this t is tf, right? And tf we know, that's expression 2, so substituting in 2, then we find that theta f is given by mu m prime g over little m a times what v0 little m over 2 mu m prime g all squared. Right, so now we know both theta f and we know the torque. So we can calculate the work done. That's torque times theta f. So this is going to be given by the expression for the torque, which is a mu m prime g multiplied by all of this stuff there. So permit me not to write that out again. And if you look at that, you find that lots of things cancel, and you end up with a very simple expression, which is a quarter m v naught squared. Okay. So that is already a nice compact and convenient answer, but we can get further understanding by manipulating this further. We can write this as a half times I v naught over a all squared, where I is what I has always been. I is just a half little m a squared. So you see those two expressions are identical, and v naught over a is omega squared. So the work done, so this is nothing more than the energy of the wheel, the rotational energy of the wheel, right? We had this expression somewhere up here. So the work exerted by the torque over the wheel slip is nothing more than the total rotational energy of the wheel, which is what we would have hoped to be the case. Good. So this brings us to a tearful end to rotational motion, at least for now. Now we're going to switch gears to something completely different, which is a branch of mechanics which was developed by many people, but in particular these two gentlemen. So Joseph Louis Lagrange and this Irishman William Hamilton. Okay, so there they are. And we're going to be focusing first on what's called Lagrangian mechanics, and this will take most of our time. Hamiltonian mechanics is a development of that, which we will briefly survey during, I think, the final two lectures. But most of our discussion is going to be on Lagrangian mechanics. So what is this? Well, this is a very effective way to find equations of motion for complicated dynamical systems, but using a scalar treatment. All right, so Newton's laws, if you think of Newton's second law of motion, these involve vector relations. And we know how to handle these, but sometimes it can be quite tedious. So for simple problems, not a problem, but for more complicated calculations, you could imagine this could be a pain. Now, as we will see when we introduce it in all its glory, which will be on Monday of next week, the Lagrangian is just a simple scalar function of the system variables. And so we just deal with a scalar, and that makes life much easier. So you've already seen this when you talked about potentials and gravitational fields or E fields. You can relate the two, but it's very nice to deal in terms of the potential because it is a scalar. So we will see that when we do this, we actually completely dodge the concept of force. And this can be an advantage because in complicated situations, it can be quite difficult to identify all of the forces, especially if there's constraints in the game. So the Lagrangian mechanics, as I hope to convince you over the next week and a half, is actually a very, very elegant and powerful way for solving problems. And it doesn't actually stop with mechanics. The idea of the Lagrangian has then taken root and is applied to many, many other areas of physics. So one finds Lagrangians used in relativity, in electromagnetism, in quantum mechanics, and quantum field theory. So for example, this on a mug, you can buy these mugs at CERN, this is the so-called standard model Lagrangian, and don't worry, this won't appear in the prelims exam, but what this does, this expresses very compactly the whole of physics apart from gravity. So all of everything in physics is we know about is somehow expressed in this compact form. So even if you don't know what each of these things is yet, I think you'll agree this is very elegant. So this is to do with the fermionic fields, this is the Higgs potential, etc. Of course, this is each of these terms can be expanded. So here's that same thing with each of those terms written out in a little more detail. And these terms can be expanded further. So this is everything written out, and you can, if you're sad enough, you can buy a T-shirt and walk around with these things on it. Okay, but as I said, this isn't. This won't be for the prelims exam. Okay, but I want to convince you that Lagrangian mechanics is a big, big part of physics. So today I'm not actually going to get as far as writing down the Lagrangian, but I'm going to do something initially which is related, which will at least give you some sense of where we are going. All right. And this is to show you that if you, because the Lagrangian, as you will find out, is when you write this down, it's related to the energy of the system. And I want to show you that already if we write down the energy of the system and make some manipulations, we get some familiar results dropping out, which you might not expect to be the case. So let's consider first conservative force in one dimensions. So the energy is given by E equals a half mx dot squared plus u of x, okay? So this is the potential. Now the energy is conserved. We will give that, which means that dE by dt is equal to 0. So let's therefore differentiate this with respect to time. So on the left-hand side, we're going to get 0 because E is a constant. Then we're going to get, differentiating that first term, we're going to get mx dot followed by an x double dot. I hope you agree. And then this, the potential, I mean, it's, I mean, in general, I've written here just as a function of x, but it could depend on other things. So let me use a partial derivative, so plus delta u by dx x dot. Okay, so because it doesn't explicitly depend on time, so using a product rule, so I've written this as du by dx multiplied by dx by dt. So I hope this expression is clear. Now we know so it's a conservative force so F is going to be given by minus du dx. So what we have is that naught equals, we have x dots everywhere, so let's take that out. And then mx double dot minus minus the force. Okay, so we get that F equals mx double dot, which is a very familiar expression. That is Newton's second law. But what is surprising, remarkable even, is that this we didn't start with Newton's second law. We just started with the conservation of energy, and we ended up with this. Okay, so let me show you just the same thing for a more concrete example. So let's take a simple 1D spring undergoing simple harmonic motion. Bless you. I've not been to China recently, I hope. Okay, so there the energy is given by a half mx double dot squared. That's the kinetic energy of the mass on the spring. And then there's the potential energy, which is given by a half kx squared. So this is the familiar expression for the potential energy of a spring coming out of Hooke's law. So let us again differentiate this with respect to time. So dE by dt, which is the left-hand side, will be 0 because it's conserved. So we end up with once more mx dot x double dot, and differentiating this we get plus kx x dot. So the same thing. So this is just the same as before, but it's a concrete example. So we take out x dot mx double dot plus kx, and so we get x double dot is equal to minus kmx. So this is the very familiar equation of motion. seen this 1,001 times, but let's be clear. Again, we got this not from Newton's second law, but we got this from just energy considerations. So I want to emphasize again, I haven't yet written down the Lagrangian. I'll leave that treat for Monday, but it will be very closely related to this, and you'll see that in these relations there's some very profound truths which are buried. When we get onto Lagrangian mechanics, there's a fair amount of jargon, so there's words I just want to flash past you now, and I write them down here for the record. Some of these you'll see a lot, some of these you'll hardly see at all, but let's just go through them so it's done with. Okay, so one talks about, for a system, generalized coordinates, which is a set of coordinates, and we'll generally use q subscript k, which can be a function of time that specify the system. So these can be x, y, or z, or they can be angles, for example. Degrees of freedom. The number of degrees of freedom is the number of independent coordinates that is sufficient to describe the configuration of the system uniquely. So it would generally be, you would just count up how many of these things you needed in your x, y, or z, or angles that you need in your problem, and this would constitute the number of degrees of freedom, except if there's a constraint which actually relates two or more of them, and then the number of degrees of freedom would actually be less than the number of coordinates. And I'll show you an example. Yeah, I'll show you an example here. So just this ball rolling down. We just need a bit of board here. So a ball rolling down this slope. Let us write down what the energy is. So the energy is, it has the translational motion, and it has rotational motion, and it has potential energy. So there's a half mx dot squared plus a half I theta dot squared. We saw this yesterday, I think, minus mgx sine alpha. So this expression specifies the energy of the system, and it looks initially, I mean, there's two generalized coordinates. There's x and phi. But what about number of degrees of freedom? Now, if we impose that the ball does not slip, then there's a clear relation between x prime and phi prime. So x prime is r phi prime, and if you can integrate that, tells you that x equals r phi. Okay, so we have. So we can then, I won't actually do it, we can rewrite E in terms of x and x prime, okay? And this is a constraint. So we have, so if we do this, and I'll let you write that expression in terms of x and x prime, we have now only writing it in terms of only one generalized coordinate, so we call this q1, which is equal to x, and we'll have a derivative which is q1 prime, which is x prime. Okay, so these are generalized coordinates, q with a subscript, and once we've written it in these terms, there's only one of them. So we have 1 degree of freedom. Now, so we initially, it seemed like there were two, but there's a relationship between the two, which we call a constraint, which enables us to reduce the problem to 1. Okay. Let's consider a second case. So we have this pendulum, which is a normal pendulum, but it's actually on a trolley which can move backwards and forwards. So we need to worry both about x and we need to worry both about theta. So the pivot coordinates are x, which can vary, and some y, which is fixed, okay? So it's x0. Now the pendulum, so the coordinates of the pendulum bob will be at, if you think about it, x along, and then if this length is L, then you have a L sine theta. So x plus L sine theta. And then the distance downwards in y will be minus L cosine theta. Okay. And so just to write down what E is, E equals a half. So the total energy will be given by the kinetic energy of both of these guys. So for this first mass here, so I didn't point out we have a mass here, so it's a half m1 x dot squared. Then we have the kinetic energy of the second mass, so it's a half m2. So we must allow for the kinetic energy both in the x and y direction. So this is the, I'll just write d by dt of x plus L sine theta, all of this squared. There's no need for us to actually write that out. And then there'll be a contribution from the y case. So that will be d by dt of minus L cosine theta all squared. Okay. So in this case, the problem very much has two generalized coordinates. So we have here 2 degrees of freedom and coordinates which are x and theta. Right, so we are starting to get some sense of where we're going, I hope, but I hope all will become much clearer very rapidly. So on Monday we will actually introduce the Lagrangian, so I'll see you then. Okay, thank you.
Why didn't we consider the translational energy of the wheels when we calculated the change of velocity?
Because that is